Okay.
So we're very happy to have
Syddansk. I can't pronounce it.
to talk about Langlands and
Yeah. Yeah. Okay. So maybe I'll write the title. Remarks and questions. Geometric Langlands. Homological mirror symmetry. So I should preface this talk with saying that I know very little about geometric Langlands or any kind of Langlands. So I'm going to tell you some facts, but I don't necessarily know who they're due to or this kind of thing. And let me, whenever you discuss geometric Langlands, you have to set up some certain amount of notation, and so I'm going to do that first. So this is a review. Ideas from geometric Langlands. Okay, so first of all, what is this about? You begin with some G, a reductive group. And if you don't want to know what a reductive group is, you can just take GLN. And then you have to take G, kind of Langlands dual group. Also reductive group. And if you began with GLN, it will still be GLN. Maybe just some brief remark about like what is this Langlands dual group, just so you know what it is. So a reductive group always has some maximal torus. And once you have this maximal torus, you can make the characters of this maximal torus. And in particular, you can ask in the adjoint action, for the adjoint action of G on its Lie algebra, what characters appear. Those are called the roots. And you can make the co-characters, and you can take some appropriately normalized dual, which is called co-roots, and the Langlands dual group for a given group. So it turns out, if you look at the classification of reductive groups, then it turns out that so of course it turns out there's, like, if you take the dual torus, then for the dual torus, the characters and the co-characters are interchanged. So you have x dual of this kind of dual torus equals characters of the dual torus, characters of the torus. And the nature of the Langlands dual group is that if you take the roots for the original group, then those are supposed to be the same as the co-roots for the Langlands, the co-roots of the Langlands dual group. Okay, that's and it turns out, if you look at the classification of reductive groups, that somehow some involution on the reductive groups. And what the subject of this Langlands duality is about is like somehow what's relationship about questions. If you have some question in representation theory about a G, how do you turn it into some statement about G Langlands dual? Okay, in some way that some elaboration upon this duality. And what is this duality? It has something to do with Fourier transform. So that's the what kind of thing this is about in general, and specifically what it's about is so what is Langlands duality about? It has to do with, you look at representations on the one hand of, you take this group G and you look at its adelic points for some field, and you look at representations of that. Representations of this kind of thing. And that's supposed to have something to do with maps from the Galois group of the absolute Galois group of the same field to the Langlands dual group. Okay, that's the kind of thing which Langlands duality is about. No one has any idea how to prove any of that, but and what is geometric Langlands about? Well, it's, you take this field to be the function field of a curve, and you study the advantage of doing that. So it's like when you study this kind of representation theory, you look at, in particular, you're interested in the representations which come from double coset spaces, like kind of symmetric spaces of this original group. And the significance of this geometric context is that those symmetric spaces, they get a geometric identification, namely as the kind of bundles on this group. So you on the one side, you study G bundles on a curve. This is some kind of and you study this because it's some kind of a symmetric space for this G, the function field of a curve. Okay. And is supposed to be related to, well, in this geometric situation, this this Galois group of the function field of the curve, it has something to do with the fundamental group of the curve. Like the fundamental group of the curve sits inside Galois group of the function field, and the rest of that we don't talk about. So the thing on the other side is somehow representations of pi1 of the curve into G Langlands dual. Okay, and now you have to say what the relationship between these things. So I said it's supposed to be some relationship, like what relationship, and what that relationship turns out to be. Well, there's various versions of it. And so like the some version which is the Valence and Drinfeld version. And before this Valence and Drinfeld version, and it's going to be in a second corrected in a way due to Rinkin and J-Story. And before this Valence and Drinfeld version, there was previous work by Drinfeld, Beaumont, Deline, all those guys. But what the relationship is supposed to be is you take D modules on this thing, and this is supposed to have something to do with coherent sheaves on this thing. And that makes sense in this geometric context. The whole point of passing this geometric context, not the whole point, but the virtue of this geometric context is this is not just some kind of set, it's an algebraic variety, or more precisely stack. So there's some kind of stack, and you can study its D modules, you get some category, and this geometric Langlands conjecture, Valence and Drinfeld, it says that it's equal to this category. Isomorphism category. So actually, that turned out to be not exactly correct, and you have to correct this in a way that's explained by these guys. You have to write one more letter, and somehow I'm not going to discuss about that. Because in fact, I don't want to so much, sorry. And now I have to say something. Actually, this is not what these guys said. These guys, they replaced this. So this statement would not be correct. These guys replaced what's in here. In this original Langlands business, it's like this is not a space. It's just some collection of items. When you make it a space, you have some choices about how to make it a space. And in particular, you have, you may know that like a locally constant sheaf is the same as vector bundle with flat connection. But the algebraic varieties that parameterize those things are different. And this statement is not this. It's the other one. It's connections. It's connections, flat connections. Oh, wait, I'll call it flat connections. Okay, so that now is this version. I'm not going to talk about this at all. But I write it to differentiate it, in, like to distinguish it from what I will discuss, which is a different version of this geometric Langlands, which is called somehow, Betty geometric Langlands. I won't put quotes, it's called Betty geometric Langlands. And it's called Betty geometric Langlands. If you call this one Betty, you should call this one Durham. So let's call it Durham. And this one was introduced by Nadler and Ben-Zvi. And so it says something fairly similar. So this one says sheaves with nilpotent microsupport. This n is not that n on the same bungee curve equals. So, by the way, I'm not going to be careful about distinguishing the category from its co-completion or whatever. So that people write in co here, I'm not going to do it. So this co again, the same n. And now you put the thing I wrote before, actually representations of pi 1. Okay, so this, and it's this version which I want to talk about. And so let me tell you about some of the decorations on here. The reason why I'm not so interested in telling you about this side is because I'm not going to talk about this side. I'm mostly going to talk about the other side. In this subject, typically this is the difficult side. What this means is that I'll tell you in a second what this n is, but this n it's something. It's a subset of the cotangent bundle of this bungee, and this means sheaves sheaves on bungee whose microsupport is contained in n. So that's what this is. So that was the very brief description about what kind of thing geometric Langlands is about. And maybe it's worth saying one more thing about this. So everyone in this picture is some kind of stack. Okay, it's like some not so well. I mean, whatever. But in particular, there are some points in this stack where it's not a stack. It's like the scheme, and there's some points where it's even smooth. So you take an irreducible local system that's with no extra automorphism, like simple, no extra automorphism local system. And this is some kind of, there's a scheme nearby. And you can ask what happens to the structure sheath. So that like take a P smooth here, corresponding to a simple local system. And to such a thing, you have the structure sheaf. And that should be some object on the other side. And the most basic question in this object is, what is that object? And that question, it goes by, I tried to distinguish these two versions, but and I tried to explain that, you know, this thing and this thing, they're different algebraic varieties, but they do have the same points. So I could equally well write that same thing here. And not only do they have the same points, like formal neighborhoods of the points are the same. So like endomorphisms, this guy here should be same as the same thing over here. And moreover, you expect that, so like these categories are different, but there's a piece of them that's the same, namely the D modules, which are somehow bounded and have a regular holonomic with nilpotent microsupport, should be the part of this isomorphic, the part of this the part of this category, which has what's called perfect microstocks everywhere. Okay, so there's some part which these have in common, and this question mark should lie in that part. I mean, the statement that these have that part in common is just Riemann-Hilbert. It's the same kind of statement that local systems and flat connections are the same. Okay. And maybe the last thing that's worth saying is that so when you have this equivalence of, so I should have put, I mean, of course, these are all conjectures. No one knows how to prove any of this stuff. Question mark, question mark. You have some equivalence of categories, which maybe you don't know how to show it exists. And you have some object, and you want to say, you want to identify where it goes. And the way people think about identifying where this object goes, everything's proven for a billion cases.
But presumably in some other special cases, like the local Langlands, that understood.
Yeah, I think local Langlands is proven. How's it? Like basically nothing is proven. Nothing of this kind is proven when that is a curve of genus at least 2, and G is non-commutative. Then nothing is known. I think it's not true. Nothing is known. There are maps, but this statement is not known.
Yeah, but this kind of statement.
Yeah, look, you should ask some expert in local language, but probably yes. I mean, I don't know. You should ask some expert in local language. It's not. Typically, more is known then. I mean, the local case somehow more or less about representation theory of loop groups, right? Of loop groups. But certainly I know nothing about it. So.
But it should be a model example. You want to think about.
I'm not going to discuss the local case. You'll see why in maybe a little bit. So I was saying, okay, how do people think about the question, where does this guy go? Well, the way you think about this question is that on this side, or on this side, there's this action where you can take a tensor product by line bundles, or more generally vector bundles or whatever, on this moduli space. Okay, and I say line bundles or vector bundles as opposed to coherent sheaves because I mean, that has to do with this writing n. But anyway, you can there's something which acts on it, and the virtue of structure sheaf at a point is that if I take a structure sheaf at a point and I tensor it with some line bundle, then that's isomorphic to itself. And so if you were to on this side know what corresponds to this action of tensor by vector bundles, then you would be in a good situation to go look for where that kind of object goes. You would look for people who, when you apply this action, they go to somehow themselves tensor something. And there's a belief about what corresponds to this. And the belief is whatever that is corresponds to the action by Hecke operators, which I will recall for you what it is about in a second. Okay, so this question, which maybe if you believe enough things, this whole business may in the end reduce down to this question, is I mean, I should say, if you go back to like the original Langlands program, this was the question always of interest. Take a simple local system with simple Galois representation, and you ask, what is the corresponding automorphic form and whatever. And this is the geometric version of that question. So we ask, where does this guy go? And that the sense in which that turns into something which you can just study on this side is you say, okay, I go look at the objects in this category or this category or whatever, which are somehow eigen for this Hecke action. They go to themselves, tensor something stupid. Okay, so that was the explanation about why we are interested in the question of identifying Hecke eigen objects. Okay, good. So now I can cover these things up. So So one thing I owe you from that discussion I covered up is, so remember the side I'm interested in, maybe I'll write it over here. I'm interested in sheaves, microsupported in this nilpotent cone. I owe you an explanation of what is this nilpotent cone on this bun G of this curve. It's a category of interest, and it's I want. Hecke eigen objects. So first of all, what is this N? Maybe I'll explain it to you. Nothing I say will be interestingly different for GLN versus any other group. So sometimes I explain just for GLN. So to explain what this nilpotent cone is, it would be helpful if I somehow recall. I want to say something about like what is the Hitchin Langelau space. So let's consider like what is the cotangent bundle of bungee? Well, okay, so if I have a given G bundle, and let's take G to be GLN, so it's just vector bundle. If I have a given vector bundle, so E vector bundle, and then I could ask, like, what is the tangent space at E to this bun GLN C? Well, if you do some deformation theory, you know it is X1, maybe X star X1. E. And so duality tells you that this is HOM from E to like E tensor the canonical bundle of the curve. Dual. Okay, that's what you learned from state duality. You learn that this thing is, at least somehow it gets points, are So here it's like hom EE, but in general, it's somehow like the sections of the adjoint. Let's discuss GLA. It's pairs of E together with a map from E tensor KC. Okay, but there's some similar thing for general G where you replace hom EE with the adjoint bundle. So okay, so this is what's this is what is what this the point the points of this cotangent bundle are these things, and this is what's called the Higgs bundle. I have no idea what that has to do with like this word, the same word in physics. Anyway, it's called Higgs bundle, usually this is given somehow. It's called phi, and there's a map where you take the characteristic polynomial of phi. Or you say the same thing in some more obfuscated way for other G, and you get how to say it? Somehow an n section of T star C. Okay, where that n section in each fiber of the cotangent bundle, you record the eigenvalues of phi. So these things are called a spectral curve. Spectral curve. And this n, it's called the global nilpotent cone, and it's just the locus where phi is nilpotent. This is contained in this T star phi C. This is where phi is nilpotent. Okay. So at some locus, and if we know, I mean, it's a fact originally due to Lemon that this is a Lagrangian. It's a conical. It's obvious that it's conical, and it's Lagrangian. So it's a kind of thing with quite reasonable. Maybe I discussed a little bit what Microsupport is about. But if you know, it's the kind of thing which is quite reasonable to study sheaves microsupported. And I think it's certainly a belief and maybe a theorem that this kind of Hecke eigen objects have to have this nilpotent microsupport. But anyway, that's what is this n. Okay. And then maybe I should tell you a little bit more about this map. Hitchin. We'll come back to that. This is called Hitchins integrable system. And if you haven't before seen anything about Hitchins integrable system, okay, it's some map from this space to that space, and the one thing which is helpful to know about this is that if you take a curve which happens to be let's say reduced, irreducible, smooth, smooth, the fiber over such a thing is more or less its Jacobian. So this is the, I mean, any kind of integrable system means, I shouldn't have called this C because that one was already C. Maybe sigma. So you have some kind of picture where you have you have your original curve C, and you have some kind of multi-section of C called sigma, and the statement being made here is if you have if you have some kind of Higgs field, it's E phi E tensor KC, then it's like having this kind of thing on C corresponds to a line bundle on sigma. Okay, that's the statement. And what is the correspondence? Well, I told you that sigma, it's about the eigenvalues in each fiber of, so in some fiber, these are the eigenvalues of phi. And the line bundle, well, it's the eigenvectors. That's what this corresponds to. Okay. So now we come back to this business of Hecke, Hecke correspondence. No, I'm not saying the Jacobian maps to the curve. I'm saying the Jacobian is the fiber. Yeah, sorry, maybe that was confusing. I'm not saying the Jacobian maps the curve. This is an element of this set. And like this particular multisection is an element of all multisections, and the fiber over that particular element is its Jacobian. So the reason why this, I now have to explain about Hecke operator. So there's kind of Hecke correspondence. So I just explained to you the simplest Hecke correspondence. There's many of them, but I explained the simplest one. So let's have Bun. I'm just going to write Bun now for vector bundles. That's a fixed rank. So we have Bun and C, and then I have Bun and C across C. And the Hecke correspondence is something which maps to these things. And what maps to these things? Well, I should take one vector bundle. Yeah, sure. And yeah, I just discussed GLN for a while. To go from at the level of discussion I'm having, to go from GLN to other groups, you have to just input your knowledge of representation.
Vivek, sorry, before you go there, are you going to tell us what the geometric significance of the slopes of phi is important in the future?
Phi being nilpotent means sigma is sitting just on top of C.
So sigma is just copy of C.
Yeah, it's just all. Because nilpotent means all eigenvalues 0, so means that this sigma is just the n-fold thickening of C. So maybe in other words, it's like sigma. There's one point of, yeah, maybe I should have said the space of n sections of T star C. It's like a vector space, and this vector space has 0, and this nilpotent cone is the preimage of 0. So about this Hecke correspondence, it's I should pick up a vector bundle from here and a vector bundle from here and a point in C. And Hecke correspondence is about, I should pick up those such that E restricted to C minus this little c, isomorphic to F restricted to C minus little c. Okay, this is Hecke correspondence. And just to make it maybe a little, just a little bit more specific, let's take rank n bundles of degree d. And d, I mean, such a correspondence either increases the degree by 1 or decreases the degree by 1. I mean, we could do anything to the degree, but I'm going to take the ones that increase the degree by 1. It's not important. All of those things are Hecke correspondences. This is an example of Hecke correspondence. If these things increase degree by 1. From the Hecke correspondence, so let's call this H. So this H, it's some possibly singular locus in this product. And on this possibly singular locus in this product, you can take what's called the intersection cohomology sheaf. It's some particular sheaf you can associate to any variety. And having a sheaf on the product gives you an integral transform from sheaves here to sheaves here. Okay, you pull back, tensor, push forward. Yes. Integral transform. And it's known to preserve. I don't actually know who this is due to. It's due to ignorance. Okay, and nilpotent microsupport. So this fact is due to someone, maybe Drinfeld, maybe someone else. I don't know who it's due to. If you want to know, ask David Nadler. He'll tell you. But anyway, some correspondence. So we have a map from sheaves and bun is n d to sheaves and bun and d plus 1. I mean, of course, these are different spaces, but so to you know, that's just sum over d. I mean, bun n is the sum over d of these things, and what does it mean to be a Hecke eigensheaf, at least for this Hecke correspondence? It means I should take this I, C, H, and I ask what happens when I apply it to my mystery sheaf F. So, sorry, I wrote the wrong thing here. This times C. And sheaves on this product is the same as this. So I asked that when I apply this Hecke correspondence to this F, what does it mean to be Hecke eigensheaf? Like, what does this mean? Let me finish this. What does this mean? It means I apply this thing, well, and then I get back this F tensor L, where this L is an element of there. And maybe I just to decorate it, and this is called the eigenvalue. No, sum. I just summed over all d. Yeah, I mean, you know, like this is a different space than this.
Were these the first term class?
Yeah, these first term class. Okay. I mean, it has to, like these are different connected components of bun n. It's not important, but I mean, you know, like it'll be important in a few seconds.
Sorry, what's can you what's happening here?
I'm just
I
explaining.
don't understand
Maybe union D, union over D. I just collect them all together.
overall D.
Yeah, overall D. I'll just remove this. I just collect them together overall D.
So you're saying our original space is reducible by it has all these components.
Yeah, it has all these components, different Chern classes, and you better put them together to make sense of this notion of Hecke eigensheaves. Because this Hecke operator, I only emphasize this because I'm going to get confused about it in a few minutes. This Hecke operator, it changes the degree.
But on the other side, when we talk about local systems, is there such grading as well? But very people start about where does it turn out from?
So this is a technical aside which we will not return.
Okay.
But I'll tell you what the answer is, which is that components here. So here there's some kind of stack, okay, and it has a gerb. I mean this stack has is everywhere non-trivially stacky, and that everywhere non-trivial stackiness has to do with the center of this group. So in the GL case, there's a BGM everywhere, and you can break this category by characters of that BGM. And characters for the center of the dual group is the same as connected components, like possible values of this Chern class.
So we really have a whole family of statements other than if you want to.
You can break it up into the pieces, yeah. But maybe it's so something which maybe this is good to say now. Something which I wish I had a better idea how to say this business about eigensheaves just one component at a time. And certainly there is such a way. I mean, it is just my ignorance. Okay, this is not an ignorance of the subject, I think, because I could just take the Hecke operator, which increases degree, and the one that decreases degree, and compose them, and I could study that operator. What is not immediately obvious to me is whether being eigen for that operator or some collection of such operators implies you're eigen in this original sense. Probably, anyway, I'm a little bit confused about that. I'll come back to it in a second when I explain why I'm going to care about this. Okay, so there's Hecke eigensheaf, and there's eigenvalue. Okay, so this was still kind of the review. It's the same thing. Yeah, just the same correspondence. I see. I mean, I never studied geometric planets. Okay, so it somehow you shouldn't assume anything I tell you is about that is correct. I mean, this is more or less a correct definition. But for example, you could ask me, well, do I mean that they just are isomorphic or I fixed isomorphic? I have no idea. It's basically irrelevant for anything I'm going to tell you. I'll explain why it's irrelevant. It's irrelevant because them just the being isomorphic makes it a subset of this product. Fixing an isomorphism gives you something with a map. That map's going to be proper. If the proper push forward of IC sheath is IC sheath maybe plus some nonsense by a decomposition theorem, so it just doesn't matter. In fact, always with this kind of stuff, you can't get it too wrong because you write down some Hecke functor. If someone else wrote down some different one, the difference is going to be also some Hecke functors. So the notion of eigen is not so. I mean, what the eigenvalues are is maybe somehow slightly sensitive, but whether it's eigen or not sensitive.
And the sum over D is infinite.
Yeah, infinite, yeah. It's not important that it's infinite because it's not like really, like how to say, the component that's like bun n is isomorphic to the bun n 0 component. So it's not like infinite in a really meaningful way. Okay. So this was about so now I want to explain to you why why Hitchin fibers should give sheaths. And this is some kind of geometric fact certainly known to Behlens and Drinfeld. Somehow this kind of incorporated in this Kapust and Witten papers recently. I think Donaghy and Pantev are somehow also using it in their work on this subject. And the reason is these quotation marks are important. I mean, I emphasize them, sure. So the reason is the following. I mean, in this case, it's going to be, I think, a rank n local system. Right. I mean, okay, this statement is without rank, but this in this case, it's going to be a rank n local system. You'll see actually very shortly why. Not how to say, like for the Hecke operators, there are more Hecke operators whose eigenvalue will be like some, Shor function of that rank n local system. But the basic one has some rank n. You'll see why in a few seconds. So why Hitchin fibers should give eigenvalues. I'm going to consider some now some version of this in T star bun C times T star bun C times. Yeah.
The statement about the support on this notebook component one. Can you say this again?
I haven't said much about it. I've just said you take sheaves which are microsupported in the nilpotent cone. I haven't told you what microsupported means. It's not relevant yet.
But basically, in this,
we
are degenerating it on this nilpotent cone is separating sheets.
Yes.
Yeah, and these guys. So once it separates into sheets, then you can have non-trivial deep, right? I would imagine the weight from that. Is that
what? No, you can always have non-trivial T.
So,
Uh,
okay, so again, so you say that this transform preserves the microsupport. What does that say?
So I haven't told you what I'll just say what microsupport means. It's also confusing because there's stacks and so on. But the word microsupport, it means kind of the places in the, if you have a manifold and you study sheaves on that manifold, then microsupport is the directions in which the sheath is changing. So like a local system has microsupport only in the 0 section. A constructible sheath has a microsupport kind of the conormals of the stratification. And this is saying that whatever kinds of sheaves we consider, they're only allowed to have microsupport in this nilpotent cone. I will later translate this statement into something more palatable. So you can just ignore it for the.
Structure sheet of a point is microsupport at a point or transfer.
Its microsupport is the conormal to that point.
Okay.
Yeah. So if you explain why Hitchin fibers, in some sense, should give eigenvalues. First, let me, so you can write a similar thing to this one. And so like, what is the similar thing? I should take this kind of E phi, F psi, two Higgs fields, some C, such that E restricted to C minus C is isomorphic, I mean, isomorphism of pairs. So E phi isomorphic to F psi on C minus C. Right, that's just the exact counterpart. And what so we'll translate this in a second. What does this mean? It means E is isomorphic to F by an isomorphism that sends phi to psi. Okay. What? Yes. Yeah. So this shouldn't have been just a C. I should have called this a C C. This is a point in T star C. And then so I've at the moment only explained the map to C. And let me explain about this map to T star C. So so to explain that, if E and phi isomorphic to F and psi away from some C, that means in particular they had better have the same spectral curve. And moreover, the corresponding line bundles had better be isomorphic. Okay, now, and if those vector bundles, if they differ by somehow 1 degree, then the isomorphism on line bundles, I should be able to extend it except at 1 point. And that's the point C. So maybe I should have said not this may be a condition or it may be automatic, and this kind of the corresponding line bundle corresponding to E isomorphic the line bundle corresponding to F away from sigma minus C. Okay, so that's some locus. And again, you can do this kind of thing of whatever. So I don't want to take any sheaf on it actually, but it's some locus. Let's call this a script H. And some kind of fact, which is some kind of again some kind of like deformation theory calculation, is that at least at smooth points of like both this kind of H, let's just say generic points of H, this script H is the co-normal bundle to H in this cotangent bundle of bun and D times bun and D plus 1 times C. So this is some classical fact that actually I don't know where to read this fact, but it's some classical fact. Okay, and so what is the significance of that?
So I don't understand. So one is this pretty chronological. You said that the condition for example is still outside of C. Spectral curve.
like if you scale phi and you scale psi and you scale the spectral curve, it's just scale it. Okay. And so what is the point? Well, so if it okay, like first the geometric fact. Okay, so if you okay, let's call this pi 1 and this pi. So the geometric fact is that if I were to take pi so choose some this like sigma C. So choose some spectral curve, and I'm going to write this J sigma the corresponding fiber of the Hitchin fibration. And the geometric fact was obvious from what's written there, is that if you are to take this kind of pi 2, pi 1 star inverse is J of sigma, you can pull it back. In other words, you study bundles. What is this J sigma? This is those Higgs bundles with fixed spectral curves. So you study these things, and you intersect it with this curly H. What is that? That's those vector bundles which begin with this spectral curve, and then like some Hecke modification of them along the spectral curve. And then I push it forward. And obviously, this is equal to, again, this J sigma times sigma. Okay. So it has this the J sigma this J sigma has some kind of itself eigen property with respect to this this Hecke correspondence. You apply it, and then you get it back at times sigma. I mean, inside each component of bun n d, it's one component, and then like one for each d. Yeah, I mean, this will be the component in d, and this will be the component in d plus 1, but they're somehow, you know, isomorphic. So I don't distinguish. So this fact. So what does that say? That says that if you, yeah.
What is the dimension of the components of bun and d? How does it depend on d?
Independent of d. Well,
no, bun and at a fixed d. How does it depend on d?
What?
Fixed d. You said that this bun, the t star bun d breaks up by.
I mean, bun n breaks up different components for each d. Independent of d. Depends on n, of course, but independent of d. No, independent of d. There's some formula which I don't remember, but with some formula.
But it's not a
Yeah. I think when n equals 2, I don't remember the formula. Okay, so here you see some kind of eigen property. And what that teaches you is if you have some way of turning J sigma into an into an element of this thing, so that applying applying this Hecke correspondence, this Hecke functor, has the effect of convolution with its conormal. Then you will have produced yourself some kind of eigen object. Okay, I say this vaguely at the moment. I try and make it more precise later on. This observation was presumably why Valenson and Drinfeld decided to produce Hecke eigensheaves by quantizing the Hitchin system, because what does quantize the Hitchin system mean? It means that do something which is like producing things associated to fibers. And also, if you read this Kapust and Witten paper, similar idea plays some role. They want to produce, some kind of idea is that this J sigma should somehow or other give you an eigen object. This is why it will give you an eigen object. It's always the same explanation. But the question is, the mathematical question is, can you produce a mathematical theory which actually, has the following properties? It should have the property that you can get a sheaf from J sigma, and it should moreover have the property that this thing should be true. And yeah. So that's our task now. Somehow, how close can we get to producing such a mathematical theory? No, this is a true statement, but I have not yet. So question. Let me just write this. Question: can one produce an element of now this thing returns the sheaves and Bungie from the Lagrangian J sigma. Let's call it F sigma, an element F sigma of this thing, such that perhaps because of this reason, F sigma is an eigensheaf. So, like for example, the kind of thing which would make this true. What? That's another question. We discuss all these questions shortly, but a thing which might make what satisfies a formula for like this? Well, sheaves and their microsupport. Okay, that's one such thing. So if it were the case that I had some kind of sheaf theory for which I could have a sheaf whose microsupport was this thing, that we don't know how to do at the moment because this is not exact. But okay, never mind. If I had some such magical theory, then I would expect this formula to tell me that if I put in some person whose microsupport began life as this J sigma, then I apply this Hecke transform, and the microsupport of the resulting object would have this kind of microsupport, maybe it would have this kind of decomposition, and maybe objects with this microsupport are unique or almost unique or something, and then you could try and prove it was an eigenvalue. That's how you would imagine proceeding. This is pure fiction. The thing I said is pure fiction for the reason that, in particular, for the reason that this is a non-exact Lagrangian, and so the microsheaf theory does not. We don't have at the moment a microsheaf theory which recognizes non-exact Lagrangians, depending on whether or not you believe things Tatsuki has been writing. So maybe such a theory will exist soon, but at least I don't understand such a theory. And it will only be exact if it's inside the nilpotent cone. So then you basically, which does not help you at all, because all the difficulty is sitting in the nilpotent cone. Okay, so I hope I've made clear why this kind of philosophy, I mean, this kind of geometric picture leads you to this question of trying to produce objects from the Hitchin fiber. This is all classical. This is like a review of things that were definitely known to Valence and Drinfeld like 30 years ago, and then somehow.
Suppose you understood it really well. No.
I mean, then you would already understand this category.
I mean, I think from physics perspective, the way you want to study it is at the notebook. Like you should be able to understand that way.
There's various ways you could study things, but I'm going to study it this way.
I thought in some other work didn't you exactly study like the generation of sigma and then you somehow.
That's true. In special examples, nilpotent cone can be simple enough you can just calculate everything. But in general, it's extremely singular, and we don't know how to compute that category. Yeah. And even if you did know how to compute that category, it may be somehow non-trivial to produce Hecke eigen objects in that category. Whereas anyone you produce by any such quantization procedure, whatever that procedure happens to be, has a reason to want to be eigen. Anyway, I have nothing to say about the nilpotent cone, so that's why I continue with this. It's been maybe, should I take a break or?
We've gotten tougher since you left.
Okay, we don't take breaks anymore. Okay, fine. So,
Unless
okay.
you want.
No, I can continue. Okay, so that was all some kind of review, and now I will tell you my attempt to carry out this some part of this program, where I get stuck. So okay, so I want some kind of so we want let's give up for the moment on this question of checking that things are eigen, and first study the question of how can how am I going to produce sheaves from Lagranges? Okay, sheaves from Lagranges. And I think there's maybe 3 ways of doing this that that people know, which it's possible they're conjectured to be equivalent in this setting. There's 3 paths you could take. One path is quantization. And I think this has something to do with what Valence and Drinfeld are doing, which I don't understand. Anyway, it's not what we're going to do. There's another path. No, just like you know, if you have integrable, I mean, in the old days, if you have symplectic manifold, it should give you like something, and Lagrangian in it should give you like object of that thing. I'm not going to discuss it. And there's another thing which is somehow, there's a way of using non-abelian Hodge for this. And this is pursued by Donaghy and Pantev, and I won't discuss it either. And maybe I'll discuss it later, but I won't discuss it now. And the thing that that I will discuss is flare theory. So why, in what way does flare theory tell you anything about getting objects from
Are there some hyperkähler setting?
yeah, well, some hyperkähler setting. So I mean that's why this kind of Kontsevich belief is supposed to identify these at least maybe these two. I'm not sure about this third one, but yeah, maybe they're all supposed to be the same. Okay, so maybe I'll just state that. So some theorem, and this is a theorem of myself and my collaborators. Theorem says the following. It says that if X is what's called the Weinstein manifold, with a skeleton lambda, then the Fukaya category of X, the wrapped Fukaya category, is isomorphic lambda. I don't want lambda. L, isomorphic to microsheaves on L. There's some ins and ops there. It says this. So you can use this tool. You can use this as a tool for producing sheaves from Lagranges. And maybe some few words about how this works. It's just going to be a cartoon. Okay, so here's X, and then here's L, and then L has what are called co-cores. They look like this. Co-cores. And roughly speaking, you produce, given given some kind of given some Lagrangian M, you produce the microsheaf on L by testing it against these co-cores. That's roughly speaking. But you may ask, why am I giving you such an abbrevious cartoon? The proof of this theorem is at least 300 pages. Okay, so I'm not going to explain it to you here. Okay, so there's a somehow this is not so useful for this purpose, for this purpose, at least not immediately, because the category we studied here was the category of exact Lagrangians. And I just finished discussing that those things are definitely not exact Lagrangians. So we cannot directly apply this theorem and get going. At least not as stated. But okay. Corollary. Also true for if you allow non-exact Lagrangians and work over the Norway quadrant. The proof of the corollary the diagonal in x cross x is exact. So, therefore, if how to say the diagonal in the product, it corresponds to the identity functor. And whenever I can resolve the identity functor, like if you have a vector space, and you can resolve the unit and so okay, let's just explain this statement. If you have a vector space, V vector space, and if you can write one V as sum of E dual tensor F, EI dual tensor Fi, this implies that the Fi generate V. Right, because if you take any vector you like, apply this thing, break it into the sum, you pair with these E duals, you get some numbers, and then you learn that everything is a linear combination of the Fs. So the same argument categorically tells you that if you have the identity and you can resolve it by a complex of kind of split things, then those had better generate the category, just by the same reason. And so since this is exact, I can apply whatever theory I had before to the diagonal itself. And it turns out that the ingredients of that theorem tell you that, and part of the proof of that theorem is that when you have this kind of Weinstein manifold, it's Fukaya category generated by cocores. And it's a just fact of geometry that the cocores of the product are the products of the cocores. So you learn that the diagonal can be resolved. So hence resolved by products of cocores. Therefore, it's cocores generate. And the point is that is true no matter like what kind of objects I throw into X. It's like whatever I ever try and do, as long as it remains the case that the diagonal represents the identity functor, I have not added anything to the category. Okay, so just like whatever I do, whatever I add, as long as it's still true that the diagonal represents the identity, it's still generated by cocores, so that theorem still holds. It's like generated by the exact part of the category. So it's kind of bizarre. I mean, it's a little bit confusing, but it's true.
Okay. In your side, when the Hitchin fiber is Lagrange,
yeah,
even if not exact, the failure of exactness comes from the complex structure moduli of C. Do they rotate to scale moduli? Like what are the where does non-exactness come from? Like which parameter? My variance so that things not exact. When you say Berkeley, we're not exact, right? So do you have some scale parameters? Scale parameters the complex structure I usually think about you want to do it around.
But it's a holomorphic Lagrangian. Maybe I'll answer your question in a precise way. It's exactly the same situation as if you ask in the cotangent bundle of a curve, why is this n multisection or whatever, the spectral curve, like why is it not exact? What's contributing to non-exactness? And what's contributing to non-exactness are the periods of the one form of this lambda. Because if it was exact, those would all be zero. and it's similar. Okay, so I've learned that like by this theorem and this corollary, I mean, I only stated separately because we didn't realize this for some reason. So this corollary, if you give me an object of the Fukaya category, exact or not, then I can produce this microsheath. We haven't yet gotten around to discussing what is microsheath, but whatever it is, I can produce. I mean, of course, it's going to be something closely related to sheath. I'll tell you that in a little bit. So, yes, but now I have to be slightly careful because this is true for objects of the Fukaya category. And if you have a non-exact Lagrangian, it does not for free define an object of the Fukaya category. It could be obstructed or whatever. Okay, so an additional fact, so fact, and this fact goes back some distance. But the first place I find it in the literature is in some paper of Solomon Verbitsky that proves much more. It is that somehow holomorphic Lagrangians are unobstructed. As I said, they prove much more. I think this might be true, like almost for degree reasons or something. And so this implies that again this given X, some kind of like, let's say, holomorphic Weinstein manifold. I didn't discuss even what is Weinstein manifold. And with skeleton L, and exact, not exact, holomorphic Lagrangian, maybe containing local system. I think, strictly speaking, to get an, I don't really know how to wrap Lagrangians which are not conic. So let's restrict to compact Lagrangians, which is all I care about anyway for this Hitchin business, the compact. And holomorphic compact Lagrangian M. There exists, how to say, M defines object of pi category of X with coefficients in the Novikov ring. That's why I didn't want to use lambda before, because the Novikov ring. I'll just write Novikov of, which is isomorphic to microsheaves on L with Novikov coefficients. Because we have non-exact objects. If you have non-exact object, then you are not guaranteed that the count of this kind of disk, any disk count, is finite. And so you better count them by their area. So you better use Novikov ring. Maybe you're asking why do we need the whole Novikov ring and not just the periods? You just need the periods. Okay, so now the result of this business is that from a holomorphic compact Lagrangian in a holomorphic Weinstein manifold, I get a microsheath on the skeleton. Okay, now I have to tell you what on earth, where I'm going to find a holomorphic Weinstein manifold, and what this category has to do with microsheaves on the skeleton. This takes a long time to explain. The paper I'm somehow giving a talk on is about 8 pages. So it may be faster just to read this paper. Listen to this. Okay, so yeah, so now about like fact, and this fact is classical probably due to Hitchin in the somehow simplest cases, and then somehow etc. Which is that says that T star on G, and here we're just in GLN, let's say on N. It's true for bun G in general. So, bun G of a curve, it contains so if I look at the semi-stable part, so here I guess the fact is that if you use the that somehow if you sorry, the fact is that if you use the usual definition of stability for bundles and you demand that like subbundles and so on preserve the have to be Higgs subbundles that have to respect the Higgs field and so on, and then there's some more complicated thing you have to do for general G. If you do all of that, then the notion of stability behaves well enough that this thing is a orbital. Okay, and if strictly that's going to be true only if this G is semi-simple. Otherwise, we throw out some generic stabilizers, whatever. This is basically orbital. Obviously, it's holomorphic symplectic. It's a cotangent bundle of something. I mean, it's an open set and a cotangent bundle of something complex. And has and this kind of a T star bun G C semi-stable has a contracting has how to say a C star action is a contracting C star action with well-defined limit as a T in C star. So it's not compact, but like it's like basic, it's kind of like circle compact. Now this C star action scales it down. So these facts together imply that when on components where stable equals semi-stable. So this is, for example, G like rank and degree D bundles, where D is co-prime to N. So on components like this, this T star bun G C stable is a Weinstein orbital. Okay, so whatever Weinstein orbifold is, this kind of classical facts imply that that's what it is. With skeleton, this kind of nilpotent cone intersect, kind of the stable, intersect the stable locus. Okay, so and you know these kind of Hitchin fibers over smooth points, they always lie inside this stable part. Yeah, there's this kind of annoying orbifold. No. Skeleton means the part which it does not escape as t goes to infinity. The limit as t goes to 0 will be only the C star fixed points. Yeah. But there's also some kind of things connecting between different C star fixed points, which don't escape to infinity, and that's also part of the skeleton. Maybe at the end I mentioned some like simplest explicit example. Maybe I'll just mention it now. So example, D equals 1, n equals 2. And rather than discuss all bundles of degree 1, I'll say like fixed determinant. Like fix the determinant to be some particular line bundle. It turns out the space doesn't depend on that determinant. So it's to fix the determinant. And let's have this base curve of genus 2. Okay, so this is the simplest example. Let me explain the example, then we can discuss it. So this bun. So I'm going to call this bun 2L. L is the fixed line bundle. So bun 2L C. This is some. So it's a kind of fact of classical algebraic geometry that this turns out to be the intersection. It's three-dimensional. It's the intersection of two quadrics and stable. And T. So inside this locus, there is some particular degree, I forget what, 32 or something. Some degree 32 surface. Okay, it's called the wobbly locus. We discuss what it is maybe later. Some degree 32 surface. Let's call it Z. And whatever this degree 32 surface is, it has the property that its conormal bundle away from the 0 section is smooth. And it's like projectivized conormal bundle is it's like some 16-to-1 curve of C. I mean, these are facts that either classical algebraic geometry or due to some recent people, or maybe in Donagi Panta or something. But these are just like true facts. So some degree 32 surface Z. I guess if you want a reference for these facts, there's some paper of people named Powell and Pauli, and I'm not sure if these facts are in this paper or if they refer to the papers where these facts are in, but there's a paper of these guys. what's in this paper of these guys maybe has to do with this Z. This fact is much more classical. So some degree 32 surface Z. And now if you look at T star, this bun 2L C, this stable. So it's possible, because the stability condition for the Higgs bundle requires you to respect the Higgs field, it's possible for the Higgs bundle to not, the underlying bundle to be not stable. Okay, so this thing, it contains this always, it always contains this cotangent of this bun stable, but it has more. And what more it has in this case is, so I'll just describe for you the skeleton. Okay, so the skeleton is like this thing includes in here is the zero section. And there's one other component of the skeleton. And that other component is you take the co-normal bundle to Z. That's how, like, you're the zero section, you're this co-normal bundle, and you cap it off in some way. You basically cap it off by that curve, which is the 16:1 cover or whatever. So that's the description of the skeleton in this like simplest possible case. Basis, this is 3 complex dimensional. This thing is, I guess, 6. There are simpler examples you can make if you allow punctures and then. And the reason simplest example is, you might ask, like, what if I drop the genus to like 1 or 0? Then there's almost no stable things at all, or just none, and everything is in the stack part. So there's just somehow. What? No, I didn't say anything of the sort. I said that the Lagrangian is the zero section inside this, union the co-normal bundle to this guy, and then capped off in some way. Where was I? Oh, yeah, so I was complaining about this orbifold business. So so I would really, this must be something known to anyone who's competent in this business and maybe like some representation theory, but it's not known to me. And I wish it, which components for which other groups have no orbital points. Okay, I would like to know the answer to this question. It's not essential for anything, but okay, there's 2 questions, and also another related question is, when is this orbifold a global quotient? What? No, that's not an orbifold. But for GLN, there's no orbifold. When is it a global quotient? So I think this theorem is basically fine if for global quotients by finite groups. We haven't written it, but I think it's basically fine. If it's not a global quotient, then yeah, someone should prove that theorem in the orbifold case. But it could be that for this stuff, it's always global quotient or whatever. And in any case, none of this geometric Langlands stuff is known even for GLN. So you can say something non-trivial. Okay. Okay.
So if you do not make those assumptions about the scope factors, what do we know about
no, it has a negative end. I mean, you know, like it has a negative end. It has like a hole in the bottom. It's like a Weinstein-Cobordism. Yeah, there's a question for Floer theorists, which is prove. Maybe there's a question for two people. One should be a Floer theorist, which can prove like when is this true in case of Weinstein-Cobordism with negative n, and the other person has to you know, like know enough about like what is this in the non-coprime case to say like what is behavior of the contact boundary at the negative part. Okay, so if you can do those two things, then maybe you can adapt this to the somehow not this case. Well, I haven't even said yet what you can adapt. So let me get to produce some object. I'm only going to consider. Let me do something, and then we can discuss what else is possible. But at the moment, like nothing has happened yet. Okay, so let me do something. So I'm going to collect all these assumptions into the statement that the component is good. And an example of good component is GLN coprime rank degree. Okay, so what's left to say? Okay, so I have this Fukaya. This T star bun G C stable. We assume it's a good component. And then isomorphic to and this is this GPS. And part of the proof of this GPS theorem is also some work with David Nadler about microsheaves and microsheaves on this kind of nilpotent stable part, and then there's a map from this to this kind of sheaves. And I haven't yet said anything with this map. Bun G C. Maybe it's better if I say that there's a map from microsheaves on all of n, and this is just equal to sheaves and bun G C. And there's also a the reason that there's this map, there's two things to say. Basically, the reason that this map is that whatever microsheaves are, they're a sheaf of categories, and this is an open set inside this, so I just restrict. Okay, that's the and this is some kind of tautology. But in fact, this kind of brief explanation is slightly a lie, because the definition of microsheaves here and here is not exactly the same. So you can prove in the end it's the same, but it's not a complete. I mean, you have to read a paper of myself and David Nadler for that. It's not a long paper, but it's not. Okay, so this map is more confusing than it may first appear. Anyway, it exists. And so and then there's a further restriction to microsheaves on N intersect T star bun G C stable, okay, which equals this sheaves and bun G C stable, and of course this diagram commutes. And there's and so now well, I can begin with this J sigma, an object in here, and I can send it maybe here, and then take an adjoint. Okay, that's the map. Maybe now I'll take a break, and then afterwards I have more to say about this was the first part about how to construct something, and then the second part, if anyone's still interested, I'll explain why I cannot prove this is a Hecke eigensheath, the resulting object. So maybe take a short break for some water.